So let's begin. I hope that everyone who is supposed to be here is here online. Welcome and thank you. So the topic, of course, is binaural transducers and playback systems and the binaural measurement theory and practice. So this is an update, and I hope it's still accurate, of an old PowerPoint, really, about the Head Acoustics binaural technology. And as far as I am aware right now, please correct me if I'm wrong, we have the HMS5 as the current completely self-contained digital head, which outputs by USB or AES EBU a completely equal signal, which is measurement compatible, and which then can be carried on to a Head Acoustics playback equalizer, PEQ, or now obsolete, Lab P2, etc., for the playback to headphones with correct equalization. We're going to be describing why this is important, how it all works, and in the history a little bit here, also how it came about. So the transducers, in terms of the digital self-contained, we have the history of HMS3, the HMS4, both of them now obsolete, now the HMS5, but the function and the geometry physically and the equalizations are all identical among these heads. And the only subtle difference, if you will, is that each head gets an individually measured transfer function, and there is also available a quote-unquote generic one, which can be used, for example, in the equalization column in the filter pool in Artemis Suite to put in an equalization that was omitted. For example, if somebody recorded the head linear, which they should never do, they can then apply the ID equalization or the free field or whatever it is that they need in Artemis Suite. And we recently helped a customer do that, and he said, "I am so glad you guys built this into Artemis Suite." And so am I. We briefly had a variant of the HMS3 for people who already owned them and wanted to have the low noise head capability. We did a modification with the addition of the 80 millivolt per Pascal low noise microphones and some mods in the electronics. That was a short-term thing. It no longer exists as a product, but there are several of those, and we have one here at Head Inc. The HSU3 is the head shoulder unit with microphones, 200 volt polarization, 50 millivolt per Pascal sensitivity, which is the standard HMS SVP or NVH head microphone sensitivity. We also have the HSU 3.2 with microphones only, which are prepolarized electret condenser microphones, same sensitivity, ICP powered. HSU 3.3 is the low noise HSU with the special 80 millivolt per Pascal high sensitivity microphones with 200 volt polarization. Those are not available in a prepolarized version. And they have a different detailed equalization in order to get the same result out the door, so to speak, of being correctly equalized for measurement compatibility for a free field sound situation, which is a point source in front of the head with no other sound, like a small object in an anechoic room. You have the head look at it, you then measure the response of the head and then invert that response in the equalizer, and you then have a flat response where all you need to do is calibrate the microphones, and you have a measuring microphone for a free field incidence situation. The BHM is a wearable binaural probe microphone, which has little conical pieces, I'm sure everyone is familiar with this, that fit into a human set of cavum conchae, the hollow before the entrance of the ear canal. And one can take data with one's own ears. And I can attest that if you use the BHM on your own head and then listen correctly with calibrated playback, you will get a more lifelike even than normally with a head, because it's your own ears that did the capture, and you're able then to evaluate small differences in vertical above and below the horizontal plane for sources in front. I have found my own personal experience. So the BHM 3.2 is the wearable microphone with the 200 volt polarization mics. I don't know if that is still available. And the BHM 3.3 is the prepolarized version, the ICP powered, with the 50 millivolt per Pascal mics. The headset, binaural headset BHS2, which is now an option for Squadriga 3, it was for Squadriga 2, it is for Scobold and Scope also, is something that sits over the ear. The microphones are outside the covered pinna, so the pinna transform part of the head-related transfer function cannot operate, and we'll see what that does in terms of equalization being necessary for that device. So again, with the BHS, the BHM, and the HSU's microphone only, the equalization is performed after the microphone signals get recorded, but before they get put onto a file by the recording software. You are supposed to identify the transducer, calling for the specific equalization files that came on a memory stick with that device loaded onto the correct place in the sensor definition tool. So moving along, binaural measurement theory and practice. An artificial head that models the human physiology, the ear positions, the pinna, the shape, the head and the shoulder, etc., and with the correctly located microphones can serve not only to capture and replay for a human being spatial sound situations that could be experienced provided the context is the same, especially exactly as if you were there in life. It's really uncanny, but also can serve as an acoustical measuring instrument. And we're going to see how that came about in the Mercedes work, where Mercedes discovered and funded Klaus Genuit in his doctoral work. Klaus Genuit early on demonstrated to them very accurate equalized binaural playback. Mercedes then challenged him and said, that's very nice and we want that, but where and how do we measure the signals appropriately to agree with a free field microphone, a diffuse field microphone, a random incidence microphone? And the random incidence microphone is the microphone where you have mixed sound field conditions of things coming from different directions, not entirely diffuse, not entirely free. In other words, 99% of the real world would be best approached with a single mic by the random incidence microphone and with the head with the appropriate equalization, which is very clever actually, and we'll get to what it is and why. So binaural measurement technology gives the inherent link between human spatial sound perception and technical measurements. And right now it is extremely and especially important with the whole emergence of tonality and the accuracy of the new modern psychoacoustic measurement tonality hearing model of Roland Zotek, and the importance of that with the development of electric vehicles and also quieter and quieter things in the information technology world. Important phenomena of binaural hearing become measurable, modulation effects in particular, and tonality effects dependent upon direction and source size, when you have binaural data to begin with. And this was the beginning of Headacoustics, and it has been codified much more recently in 2018-19 in ISO 12913-2, which is the second component in the three-part -1-2-3 ISO 12913 soundscape standard set, where it is required that you have binaural acquisition and calibrated binaural playback. So we're going to discuss the two requirements of binaural measurement, how you get compatibility and calibration on the one hand, and how you get listening accuracy on the other. We're also going to present factors in the choice of normalizing equalization for the measurement compatibility, and the effects of the normalizing equalization on the microphone self-noise. You get a wonderful benefit that you effectively have Dolby noise reduction on the microphones, because the dominant factor in the head-related transfer function is a huge resonance of 12 dB approximately amplification of the hollow before the entrance of the ear canal of the human ear. The pinna is a 4 kilohertz amplifier, 12 dB plus. And in order to get that back to a flat response for measurement, you have to reduce by 12 dB. And in the process, you not only reduce the acoustic effect, you also reduce the microphone and the electronic self-noise. So the microphone gets quieter, both objectively, technically, if you will, but also very much perceptually. And it gets helpful perceptually because it is exactly the region of 4 kilohertz where we require the least sound pressure in human hearing for a given loudness. So we have the biggest perceived advantage of the noise reduction right there on account of it being on account of that resonance. Headacoustics started from the first accurate listening and accurate measuring artificial head, along with its playback system, which is a critical part. You have to have both. Just making calibrated binaural measurements and then doing arbitrary things about playing them on speakers or any kind of headphones, even very good, plugged into your sound card, or even with a wonderful audiophile DA converter, you're not going to be getting the correct result by a large margin. And we'll see how and why that is. Also Headacoustics at the same time, under Mercedes pressure, if you would, and suggestion, introduced in the DOS computer world the first active listener in the loop sound quality or psychoacoustic workstation, where you could listen as you analyze and see and figure out what is actually causing the perception and then what to do about it. So Headacoustics is always and is still centered on human perception and getting hearing, especially binaural hearing, into the act of everything about sound and vibration perception. So what is the HRTF, the head-related transfer function? If you put a person in a large geodesic sphere, for example, in an anechoic room like the US Air Force Wright-Patterson Air Force Base set up, and make a sound from a particular direction, there will be a particular response at the two ears and an arrival time difference if that source is not equidistant between the two ears, i.e. on the median plane, which bisects the is vertical plane passing through the head, equidistant between the two ears. So if you figure that out for sound sources all around the sphere, you wind up with the head-related transfer function for that individual or that artificial head. If you take the response, for example, for free field on the right and diffuse field on the left, I should say, and diffuse field on the right, and make a tolerance, this is the ITU TP58, which is the information technology European standard for artificial head tolerances, you see the dominance of the common concha resonance that is up around 10 to 15, even more decibels. And so that if you then normalize to a flat response, you get this, and that is the tolerance band of the ITU tolerance. And Head Acoustics goes that much better in terms of about plus or minus 1 dB. The type 1 measuring microphone, although we don't claim it as such, it actually meets that standard to a much tighter tolerance. If you look at the right half of the horizontal plane, and this is a map from a person wearing probe microphones in the Ruhr University Bochum laboratory of Professor Jens Blauert in about 1986-87, where a flat broadband noise source was moved on a boom in the horizontal plane, that is a horizontal plane going through the ears of the person sitting in a chair in the middle of the anechoic room, and it moved from exactly in front, equidistant around, and stopped exactly behind. So the left ear response is plotted with 0 degrees being straight in front, 90 degrees being hard right, 180 being straight behind for the left ear and for the right ear. And the response was equalized so that at 0 degrees straight in front, you had a flat response. So then we can observe what is different relative to the flat response in front for any other angle. And when the source is moved around the right-hand side, the left ear is getting in the shadow for high frequencies, at frequencies higher than that which the wavelength is about the diameter of the head, i.e. around 1500 hertz. You have this big fall off of high frequency level. And it also, though, leaks around with diffraction coming around the top of the head, from the front and the back, and reforming at the ear in the shadow and giving this very weak but visible comb filter effect. If you listen to this, it would sound like a bass heavy noise with a very subtle effect going on as you move the loudspeaker on the opposite side. On the same side of the head where the loudspeaker is, you get a big increase in level at the higher frequencies, especially above 1500 hertz, with a completely different complex pattern. So if this is mapped from black at the lowest level you get from the HRTF, from this broadband flat source, to the highest level you get, it's minus 30 to plus 15 dB. That's 45 decibels. Consider that listening to tonality in an electric vehicle, you have unavoidably a human perceiver, if you will, and an extremely different response according to the direction of incidence. If the person turns the head, and I'm sure everyone has experienced this, for a low-level tone, you hear it in one place of your head, you turn your head, it disappears because you're steering the hot spots and the quiet spots of your HRTF around. So it is essential to take binaural data, especially with tonality issues, and that is the big hot button right now. Anyway, this gives a hint about equalizing the artificial head. So what is the difference? And I hope people online are going to be able to get this. If you have a microphone and a person in a situation with two spatially separated sound sources, the microphone may not notice source 1 when source 2, through the frequency range of source 1, is at a higher level. They would only notice, hey, source 2 is playing, that's all I know about. And if they play that single mic back on headphones to one ear or both ears, they will only hear source 2. But if they're there in person, they will clearly recognize the two sources. So here is a little example that Dr. Mike Blummer at Ford did a number of years ago, where he made a recording with a single microphone and then made another recording of himself saying something different but for the same duration, mixed the two together. So it's like there were two of him talking at the same time. And so here's what he said, single mic.
Without it, it would be difficult to decipher these two hearing.
Then he did it again with the artificial head at 60 degrees left and 60 degrees right.
Without it, it would be difficult to decipher these two hearing.
So you could clearly pay attention to one or the other and hear each one, whereas it's quite a struggle to figure it out otherwise. So a single microphone encodes a point phenomenon where the binaural head and human spatial hearing encodes a field phenomenon. That is a huge and fundamental important thing. Another thing that happens, because here we took the psychoacoustic loudness measurement, any of the loudness metrics, the Moore-Glasberg or the Zwicker, and this is Zwicker ISO 532-1. This was a tire noise. This is a very old example we've used forever, 35 years plus in head acoustics, where there is one tone that is at the same level as a tone at a somewhat lower frequency, but it is much more noticeable and more annoying. The reason being that it is farther up on the resonance slope, which is calculated by the loudness metric. So if it happens to be frequency modulated and is going up and down in frequency, it is also climbing and falling on the hill of the resonance. So there is an amplitude modulation that gets generated by the HRTF, causing a stronger pattern of greater annoyance to a human being. So here is that sound. And we're not going to take time to analyze it here. So when an incident FM tone in the cavum conchae resonant frequency is measured in loudness versus time, there is this co-generated amplitude modulation, whether or you take the data from a single microphone or an artificial head, because the curve is in the loudness calculation. But if you have single microphone data, you only get the co-generated AM information about the cavum resonance and nothing else. Whereas the HRTF, as we already saw a couple of slides back, is much more complicated than that. And you actually get all kinds of co-generated modulations at weaker but noticeable levels from the HRTF related phenomenon. So that is built into binaural acquisition, is heard and is measurable in binaural data evaluations. So the factors that contribute to the HRTF are the direction dependent ones about shadowing, reflection, incident pressure and reflected pressure, adding and so on from the torso, the shoulder, the head, and the ear mold or pinna. And then the signal from that point goes on through two fixed sets of resonances, the ear canal transverse and longitudinal, and the big one, the cavum concha at 4 kilohertz. So these are always the same and they're always in circuit. This gives a clue that an equalization of a head for a non-completely diffuse but directional sound field, i.e. most of the real world, could be done simply by knowing and inverting the fixed part and letting everything else integrate around the sphere, which it does very well with the so-called ID equalization, which is unique to head acoustics transducers. So what Klaus Genuit demonstrated to Mercedes early on when he was discovered in 1981 by a gentleman named Christopher Landmann, about whom you will hear more in the history lesson that's coming up after this, he demonstrated an accurate geometrical binaural head, HMS1, which was a human head model with the human ear molds, and precisely equalizing to compensate for the headphone and the fact that the headphone is in a different place relative to the listener's head than the microphones were in the acquisition head. So all of that can be handled by a precise equalizer that is a constant. So Mercedes then said, that's very nice, Klaus, but we need to measure as well. We need to get measurements that agree with our free field mics, our random incidence mics, and our diffuse field mics. What can you do? So Klaus Genuit said, aha, I can split the equalization into two parts, one that lives with the head to normalize it for the sound field, i.e. make a measurement with the head for the free field source, measure the non-flat response. We know it's non-flat because the HRTF isn't flat anywhere. Turn it upside down, and then it cancels the opposite shape of the actual, and you get a flat response. Then you have the measurement compatibility. Then a playback equalizer device, the Lab P2, Lab P2 V1, etc., and the headphone that is intended for use with that equalization loaded into it provides you the correct playback. These must be used together, especially in the modern world with modern psychoacoustics and tonality issues. So the free field equalization is everything, the directional part and the resonances part, all in series, leading to the correction for a point source in front of the head. The ID is only the resonances corrected or inverted. The diffuse field is put the head in the diffuse field chamber and then invert the response you get from that. And you might think that these two are going to be identical or close to it. They are not by a large margin, except in the cavum concha, which is pretty much the same for everything. And we're going to see that here. If we look at the HMS equalizations, the free field equalization includes the shoulder bounce, and that's what this W shape is here, inverted W shape, that has to be done in the free field equalization. There's the cavum resonance, which has to be taken out of everything, 12 dB. And then we have this irregularity of the essentially grazing incidence past the tragus, which is a little piece here in front of your ear canal entrance, and then going into the ear canal. So the cavum concha is a reflector, part of the directional pattern, and a resonator, part of the fixed non-direction dependent part. So the ID equalization is invert only the resonances, you get the red curve. It's nearly identical to the diffuse field equalization, which is the green curve, above about 2 kilohertz, about 3 kilohertz actually, but we have a big divergence where there's a lot of energy between a diffuse field equalization and an ID equalization, and the ID equalization has been proven correct for the real world inside a car, etc. So I created here a random noise, pink noise, at 15 dBA at the 94 range of the head, and then I cranked it up by multiplying it by 100 so you could hear it. And we're going to notice the 50 millivolt per Pascal microphone system self noise with the microphone in free space, like you'd normally use it as a stick mic. Now we diffuse field equalize that microphone in a head, the ID equalize, we free field equalize, and we come back to unequalized. So you have a much quieter microphone, particularly perceptually, when it's in a head than when it's not. So you have an advantage there, and you can see the shape of those curves on the A-weighted peak noise spectrum.
What about the increase in noise?
There is an increase in noise, for example, in the free field equalization, because you have to apply more boost in the higher frequencies. So that's audible here. You can also, but it's still dominated by the cavum. In terms of the overall loudness, is least with any of these, in particular, the diffuse is a little bit lower than the others, but because it droops here, as opposed to the ID.
Some customers making noise measurements on.
I don't know if maybe Steve, if you can come closer to this mic.
Yeah, I'm dealing with some customers that have high level sounds in lower frequencies, but low level sounds in the higher frequencies. So what they're seeing is some elevated noise because of the EQ. How should customers be using low noise mics if they're seeing the effects of the EQ being applied at higher frequencies?
If you see the noise floor of a microphone or the noise floor of an artificial head, the noise floor of the artificial head is going to have the equalization shape on it. So if you see the equalization shape, you are uncomfortably close to not being able to use the head, or in the case of a microphone, use the microphone, because you're too close to the self noise. This is why the low noise head was created essentially for the IT industry. But right now the issue is coming up, and I'm recommending to some people working with quiet EVs and tonalities that they consider the low noise head. Because, and I'm going to demonstrate from actual recordings in the same chamber at the Aachen University with the same test object, where the two heads were on opposite sides of it in the same chamber, the improvement in the noise behavior. And unfortunately, there's low frequency rumble in this chamber, which is kind of dominating, but you can still hear the difference.
So the LN would be their standard.
Yes. So we're going to take, for that demonstration, the 50 millivolt per Pascal HMS 4, ID equalized, and the low noise head ID equalized. Identical responses. But you will see less of the, you'll still see it because it's still, by the way, 5 dBA self noise in the head with the low noise mics, 15 dBA, actually a little bit lower. I've seen 13.6 on a good day with a tailwind from an HMS head, standard SVP head. Anyway, we need to continue. The question has come up, how similar are heads? And we had Acoustics found 6 heads just at random, calibrated them, measured them, and they had this tolerance, plus and minus 1.5 dB above 500 hertz, different manufacturer years, way different serial numbers, and plus or minus 1 dB below 500 hertz. Head Acoustics is doing even better now, and as I mentioned, even though we're not calling it the class 1 microphone tolerance, all the heads are within that tolerance, but they are not absolutely identical. They're very, very slightly different. Each one gets its own individual measured equalization for that reason. So the normalizing equalizations for the HSU, the HMS 3, 4, and 5, and by the way, the HMS 2 with analog equalization, which was not this detailed, began the lifetime of the mathematically described geometric head, which came from Dr. Genowitz's dissertation on a mathematical model of the head-related transfer function. So we see with the line at 0 dB drawn in order to give you a reference point, what the head equalizations are for free field source, a single point in front, a fully, truly diffuse field, which is very rare in the real world, and the ID, which is for just about everything in the real world. So the reason for that is because the response out of the microphones in those conditions is this. I simply turned the graph upside down. So you get the noise floor improvement benefit that we've already discussed. If you don't complete the listening half of the binaural measurement chain, you cannot hear correctly at nearly every frequency, seriously compromising binaural perception. You can't hear energy density per unit area. A single microphone has no spatial information. It can't tell whether you have a noise source coming from a dot, a little tiny speaker that happens magically to be full range in an anechoic room, or if it's completely decorrelated all around you and you feel like you're in an acoustic fog. Your brain is exquisitely sensitive to that. And as a matter of fact, exactly the same sound level and spectrum will result in different loudness perceptions. The large source will sound louder and have a different tone color than exactly the same spectrum radiated from a small source in a free field condition. This is why, no matter what microphone or head you use, if you make psychoacoustic loudness measurements, you have to tell the analysis properties it was free field or it was diffuse field. And in this case, the word diffuse simply means large area source, not statistically diffuse in the classical decorrelation sense. So you hear energy density per unit area like you see energy density per unit area. You cannot say, okay, I pointed my light meter to the Sistine Chapel ceiling or the Grand Canyon, and I get so many 1,000 degrees Kelvin, and that's all I need to know. And like you get so many dBA with a microphone. If you go to the Grand Canyon and the wind is blowing subtly, you hear this marvelous effect, especially noticeable as truth if you see it too, context. The human is a data metadata system, and you have to keep context in mind. You can't make any kind of evaluation of calibrated sound playback. You cannot do calibrated sound playback from a single microphone, period. And you can't do it from binaural data if you don't have calibrated playback because of the HRTF. The human has to have and normally receives spatial information. So if we take the ID equalized head, green curve, and then we put in series with it the red curve in the playback device, we then get the sum of the two as the black curve given electrically to the HD 600, HD 4.1 headphones worn by the listener. You have to have that, and the black curve is going to be a constant, whether the head is free field and the playback is free field, the head is ID, playback ID, head diffuse field and playback diffuse field. So if you have, for example, with the HD 4.1 headphone, simply a flat amplifier and no headphone playback equalization, you get this error, which is a pretty huge error and extremely variable. Obviously, you can't evaluate tonalities and masking properly this way. So you're completely and unavoidably up a creek and extremely at risk of making bad decisions without binaural playback correctly from binaural data. So the sum of free field at head, free field at headphone playback, et cetera, as just mentioned, gives this constant curve for a given headphone type. This curve will be different for a different type of headphone. Like the headphones at a major listening room not too far from us are a different kind. They have a different end curve, but it has to be a constant. So calibrated playback, again, I'm going to underline this, is impossible from single mic data, period. And it's impossible from binaural data without the correct playback chain. That is why binaural acquisition and calibrated playback are required, are normative in the soundscape standard ISO 12913.2, which is becoming extremely important and relevant and critical in tonality assessments, psychoacoustic use in the sound quality world. What about playback on speakers? A head is a very good stereo mic. I've made various stereo recordings for speaker playback with heads, and they're wonderful, but both ears are hearing both speakers. Each ear is hearing both speakers. The sound field compresses, you don't get the full sphere. And what happens for a low surface brightness source, surface brightness is an astronomical term. If an astronomer is looking at a galaxy whose stars can't be resolved, it has a very dim surface brightness, and they can calculate that per unit area, like so many seconds of arc by so many seconds of arc has so much energy. If you hear a distributed sound that's, let's say, 80 dB weighted, coming from all around you, it seems to have a certain characteristic, and you can tell a very low energy concentrated spatial source of a squeak can easily be heard. If, however, you have speakers, all of that energy that's all around you is now in the area added between the speakers. It becomes louder because there's higher energy density per unit area, and you are probably going to mask the squeak, and you will hear fewer squeaks and think you're better off. You're not. So all the sound energy from all directions gets coming from two speakers, the area between them, a much smaller solid angle. I found that out when I was in college and started doing stereo recording. I was invited to record the dedication concert of a new pipe organ in a reverberant church. I went, ooh, this sounds good, and walked all around and said, I like it best here. So I put up my 2 Omni microphones. I got home and I played the recording. I said, oh no, it's way too reverberant. I don't hear the organ in proper balance. Now I know why. I didn't then. I wish I did. Anyway, those are important things. Speakers can work for some things, but please test. HRTF irregularities, according to where the sound is coming from, are also not properly played back on loudspeakers at all. Never use speakers as the main playback at an Artemis Suite binaural listening station. Calibrated playback is essential for decision-making in auditioning as you view psychoacoustic measurements, most critical with tonality hearing model, ECMA 418-2, and our unique head acoustics variant on it, the tonal annoyance weighting. Don't turn it up because tonality increases if you raise the loudness. So a lot of people have been commenting, and this is what's sensitized me to this issue right now. They're saying, I'm not sure I trust the new psychoacoustic tonality hearing model because I hear tonalities and I say, what are you doing? And they say, well, I turn it up, I hear it. Of course you will when you turn it up. But if you hear it at correct level, it may be at or below hearing threshold. The IT industry drove the standardization in the ECMA, European Computer Manufacturers Association Standards Organization, for the psychoacoustic suite of tonality and roughness because of the fact that OEMs who didn't know better were penalizing suppliers of hard disk drives, for example, for having too much tonality, when they had quieted the drive to the point that everything coming out of it was below audible threshold. So that doesn't matter at all if you can't hear it if you have high tonality. So if you raise the level by 10 dB or 20 dB, then you start hearing the tonalities. The psychoacoustic tonality measures that, but if you don't have anchored playback to correct sound pressure level and binaural data, you cannot hear it right. Very important. Okay, here is the example of the 2 normal SVP head 50 millivolt per Pascal mics in the RWTH Aachen University chamber. And the low noise head. And you can hear some subtle, moderately high frequency modulations here that are completely masked here. I'll do it again. So obviously the rule I talked about of playing at original sound pressure is wildly broken here, so you can hear this obviously. But in the modern world of e-vehicle development, particularly, it's time we started to bring the low noise head to the attention of the automotive clientele. Okay, so a quick look here, the normalizing equalizations of the HSU, the HMS, we're familiar with that. So what about the BHM, the BHS? So the BHS that covers the pinna requires a much simpler equalization, which is the red curve, and that is applied in the sensor definition. When you use it with Squadriga 3, Scovold, or Scope, the BHM is more complicated than the head because it fits in and replaces your cavum concha, which it partially fills, with a much smaller one, which is the inside of the cone that fits in there when you stick it on your head. So this is the equalization for the BHM. Both of those require ID playback equalization, and then you hear them correctly. So a quick discussion. The perceived loudness and tonal balance of a free field source, a point source, heard by a person, and a large area source with exactly the same spectrum and level is quite different, with the latter being heard as louder and a different tone color. So the psychoacoustic measures require you to say, is it diffuse or is it free? The defaults are free. The real world is mostly large sources, so call it diffuse. Make and save a favorite. Don't just grab it off the shelf. Single mic reproduction does not convey to human hearing this aspect. Bass frequencies in the real world in spatial sound situations in particular can sound louder and do in binaural properly presented data calibrated than they do in properly presented data calibrated from single mics, simply because of the human spatial perception and that difference. So thanks very much to Dr. Genuit and Roland Zatek, Winfried Kreber, and Georg Kaspari.